Hey, welcome back. So we have discussed the static cast operator, which is a compile time operator. Now these are referred to as operators, but of course they look like a function, a templated function. Now in this lecture, we will discuss the dynamic cast operator, which is a runtime operator. All right, so it's going to check at runtime. Have an example of the dynamic cast syntax with a type ID for the type argument, and then an expression for the actual argument, the actual parameter. Now the type ID, so what we want to convert to, must be a pointer or a reference to a predefined class or a pointer to a void. So we can cast to a pointer or to a pointer to a void or to a reference. Then the expression argument must be a pointer if type ID is a pointer, or an L value if the type ID is a reference. We can perform pointer upcasting and downcasting with this dynamic cast operator, and then runtime checks will be performed to ensure that the pointer is pointing to a complete object of the pointer type. This runtime check is an overhead which we do not have with the static cast because that is a compile time check. However, the dynamic cast is safer than static cast because of that runtime check. So for this to work, we require a polymorphic base class. So we want to have some virtual function in there, and that is basically used to deduce or compute the safe downcasting. And this is going to return null pointer if the check fails. So if we do not have a pointer to a complete object of the pointer type, then dynamic cast will return a null pointer, so we can check for null pointer. Alright, let's look at an example of where dynamic cast is useful. I have some base class. In the public section, I have a default constructor and a virtual destructor. This class also has a virtual toString function that we've seen before. It's going to print out base toString, and then we have some derived class which is going to publicly derive from base, which also has a default constructor and a virtual destructor. It also has the virtual toString function, which is in this case going to print out derived toString. But the derived class also has a non-virtual function, getMember. It has a private member, int member, and this getMember function is going to return that member. So in the main function, we may want to do something like this, where we print out derived member ears and then we can get that member. But in this case, I have a pointer to a base class, pbase, and then I allocate a derived object on the heap. So if I try and do this, pbase getMember, we will get an error. All right. So instead of doing that, we can cast. So we can pause the video for a second and attempt to finish this cast. Alright, what do we want to cast to? We want to cast to pointer to derived. And we want to pass in this pbase, which is a pointer to base. We cast that type to pointer to derived. Then we can try and do something like this. From pDerived, we can now get the member. We also need to remember that dynamic cast will return null pointer when the cast fails, so we can actually wrap this here, snippet, surround with, and do a check. So if pDerived, so if pDerived is not null pointer, then we can print this out, derived member is, and then get member. Build and run, and we get derived member is 5. Alright, so that works properly, and we can now also deallocate whatever pDerived is pointing at, because that will now point to derived as well. That is the object on the heap. So you can do this sort of check if that fails, so you can do an else, and then you can print out something like the pointer is null pointer or the cast failed or something like that. Okay, because sometimes we do not have virtual functions for every class. Sometimes the functions are virtual, but sometimes we do not have virtual functions, as you can see in this example with the derived class. And in that case, you may have to downcast, as we can see here, because we have to access from pDerived now. We access that function, getMember. Right, that is not a virtual function. Whereas if we want to access the toString function, for example, that's fine. So here we can, for example, we can do the toString function like so, and then we can also do toString down here maybe. And if we build and run, we firstly get derived toString, derived member is 5, and then we also get derived toString. So why do we get derived toString instead of base toString here? Well, remember the object that we have on the heap is actually type of derived. It is not a base class object. So again, virtual will allow us to invoke the appropriate function based on the object on the heap as opposed to the pointer, whereas with the non-virtual member functions, we have to consider the pointer. So here, that is why we have to downcast to pointer to derived to actually access this getMember function. Alright, so I've discussed this before, but this is just to emphasize the usefulness with dynamic cast, because this is going to return null pointer if the cast should fail. Now what will happen if we have this pointer to base and we have a new base object on the heap? And so here we are doing the cast. Alright, so what I'll do is, I will add an else part. Okay, so you can pause the video for a second and think about what is going on and what will happen if I build a run. Okay, so let's build a run and see what we get. Well, we actually get base toString because of course we have a polymorphic or a virtual function with the toString function, and also we have a base class object on the heap. So because of that we will get base toString, and we actually get a null pointer. Alright, and why is that? Well, I mentioned in these slides that the dynamic cast will return null pointer in the case where the pointer points at an incomplete object of the pointer type. So in this case, pointer to derived, we are trying to convert pBase to derived. So this is going to point to a type of base, and because of that, dynamic cast will fail. An object of type base is not a complete type or complete object of type derived. So that would be unsafe. You may get access violations and stuff like that. So we get a failed and we get a null pointer which we can check against here. If we did this the other way around, if we did a base pointer, we had a pointer to derived, and then we had a derived object on the heap, and we convert derived to base, and we had a pointer to base here, and we check for base, then that would be fine. Alright, you should not get this confused. You are looking for a complete object of the pointer type and a pointer to base. If you have a pointer to base, an object of derived will be a complete object of the base class pointer. Alright, if you have a pointer to base, object of derived will be a complete object of that type. So that can be confusing, but you have to remember that a derived object will have a complete part of the base class. So when it gets constructed, it will have a complete part of the base class. So even though the object itself is not base, it is derived. Derived inherits from base and has a complete part of the base class. These casts can also be useful in the case where you have functions. For example, I have the base class and the derived class again. Then in the next example here, I have this display pointer to some display function, but this is going to take in and have as a formal parameter a pointer to a base. And then I also have a reference version actually, which has a reference to a base for the formal parameter. So I'll just actually go down to main here. I have a pointer to base, and I allocate a new derived object on the heap. And then for display pointer, I'll actually pass in pointer to base. Again, this is perfectly fine and legal in C++. Then we can also do this with references. Now I would like to note that I do not recommend that you do it with references. This is just a trick that I want to show you, but it's best to stick with pointers. So for example, we can have some derived object and we can now have a reference to a base, but we can assign the derived object to that. So this is also legal in C++. We've seen some examples before, and now I'm passing in that reference to the base into the display reference. So I'll just go and look at the display pointer function. So as we've done before, we have a pointer to derived, and we are now downcasting from pointer to base to pointer to derived. So I named this parameter p base p. So pointer to base, but it's p uppercase here for parameter. Alright, then in the check here, we can check p derived. Then we can have this p derived. Remember, this getMember is actually not a virtual function. So in this way, we can also call non-virtual functions because we can do that check. And then of course we also have the virtual function invocation toString, otherwise we print out null pointer. And for the display ref, we have a reference to a base. And then we can have a reference to derived, for example. and we cast from that reference space parameter to a reference to derived. Then we want to convert, because you cannot do a check. So if you do something like this, where we check for a reference, it must have a bool type or something like that. So we want to check for the pointer, so we can convert that to a pointer. We have pointer to derived, and then we can pass in, so we want to cast to pointer to derived, and then we pass in r derived. So we have the address of here, otherwise we will get an error, alright? It must be a pointer to a complete type. We want to pass in the address actually, so we want to get that basically, and then we want to convert that type to pointer to derived. Now we can do the same thing as before. Again, in main I have a derived object on the heap, and for the reference I also have a derived object instantiated, and then to display pointer I pass in pbase, and here I actually have a reference to base as well, where I will assign the derived object for that reference, and then I pass in rbase. So let's just pull a run here. Observe that we get derived member is 5 and display toString twice, so we do not get null pointer. So again, upcasting is fine, but if you downcast, you want to make sure to use some sort of cast. With upcasting, you can often simply do an implicit upcast. However, searching for that is a bit more difficult, whereas for this, if I do cast, of course, we can find the instances where we actually cast. Whereas if you do C-style or that functional style or implicit casting, then of course we cannot search for that. So that is why I even prefer to use even static cast if I have to, because then I can search for that. And that is handy for debugging purposes. And also from a high level, as a reader, you can see, okay, here I'm doing casting, whether it is dynamic or static casting. But in any case, dynamic cast is excellent for downcasting, because then we can check whether we have null pointer or not. So just another example, again, this is handy with functions as we've seen in previous examples, because now we don't have to use multiple functions. We can simply have one function with a pointer to base, for example, and then we can downcast if we need to. Or with the use of virtual functions, we can access and use the specific function based on the object on the heap if that function is virtual. Now again, I would like to mention that I do not recommend that you actually use this reference style. Unless you have to, it is best to stick with pointers, because again, you don't now have to do this extra step to convert to a pointer. But where you have to do that, you can convert to pointer, and then you can check for that. Alright, so let's move on to a couple more examples before we wrap up this lecture. Similar to the static cast example that I had before, we have some entity 1 and entity 2, and in this case I actually do have some virtual functions, but it doesn't really matter because entity 2 does not derive from entity 1, so these are completely different classes. Then in the main function, I instantiate entity 1. Then we can cast using compile time static cast, right? We cast the type of E1 to pointer to entity 2, and we try and assign that to some pointer. Now we can also do a check with PE2, the second pointer here, because that makes sense. We have the pointer, so we check for that, and then if we have something, then we do toString. But of course, this is going to fail at compile time because those are completely different classes. So if I build, we get an error, cannot convert from pointer to entity 1 to pointer to entity 2. That is a compile time error that we get. Then we can also do a dynamic cast, and now of course this is going to be a runtime error that we get, or should I say a runtime fail. So if dynamic cast fails, we actually get a null pointer, and then we check for that. And so that again will return null pointer when it fails. So the difference with these that I'm trying to highlight is that this here static cast is going to fail at compile time, so your program won't even run with that. This here is going to fail at runtime, so the program will run and we simply have to check appropriately. The program is not simply going to crash, but dynamic cast is going to fail. So if we build and run, we do not get the toString, but the program does not crash or anything like that, whereas with static cast it will not even compile. So of course these are simple examples, but your program can get really complex in production. And in the case where you want to ensure the cast at compile time, that is, if you do not even want your program to run unless the cast will happen appropriately, then you can use static cast. Otherwise, if you are not sure of the object that you will have on the heap, so you do not know what object you will actually be assigning to some pointer, some address that you will be assigning to the pointer, then you can do dynamic cast, and then you can simply check for that at runtime. So those are the differences that I'm trying to emphasize here with this example. As I mentioned in the slides, with dynamic cast we want a pointer to an existing, so a predefined type. We do not cast fundamental types. So for example, if we had a double, and we want to cast the type double to int, you will actually get a red squiggly, so the type in a dynamic cast must be a pointer or a reference to a complete class type or pointer to void. So we cannot use dynamic cast here to cast to int. Again, you can try to build here and you're going to get a failed, but static cast works. Alright, we've seen this before, static cast is going to work. So again, just trying to emphasize the differences there. We can also cast a pointer to void. So in this example, I have two different classes again, entity 1, entity 2. Then in the main function, I go and allocate objects on the heap. So new entity 1, new entity 2. I assign those to these pointers, PE1 for pointer to entity 1, and then also pointer to entity 2. Then here we are dynamically casting from pointer to entity 1 to pointer to void. So we assign that to this pointer to void. Now I would like to note that if you use dynamic cast, remember that I mentioned we have to use a pointer to a complete class type. So with this you can actually get an error. That is with dynamic cast. So if I build here invalid expression type for dynamic cast, instead what you can do is you can use static cast. So we are casting the void pointer to pointer to entity 1, and we are assigning that to this here, the second variable pointer to entity 1, the second one here, and then we can do the check if we want as well. So we are checking if we have something, the cast is successful in that way, then we can print it out or null pointer, because if that pointer does not point to something valid, then we will have something like null pointer, for example. So here we can do something similar, but in this case we are changing that, so we are casting pointer to entity 2 back to void, and we are assigning that to void again, and then we are casting from that back again to entity 2. So and then we assign that to pointer to entity 2, and then we check for that pointer to entity 2, second version there, and then we can do toString if we want, and then deallocate. If we build a run here quickly, we get entity 1 toString, entity 2 toString. So just wanted to mention this, you can have some issues with dynamic cast. As I mentioned, you have to use a pointer to a complete class type, predefined class type. You cannot use pointer to void. That is for the actual argument, the actual parameter, but for the type you can, as we can see with dynamic cast, for the type argument you can use pointer to void. Alright, so I just wanted to mention those differences. In this next example, I have four classes here, class A, B, C, and D. And in class A, I have a virtual function, just any virtual function to enable polymorphism here. And so class B is going to publicly derive from class A, and so is class C, but class D is going to publicly derive from class B and class C. Alright, so then in the main function, I go and declare a pointer to class D. I name that PD, alright, and then I allocate an object of type D on the heap. Now we have an ambiguous cast here, so let me go through here. We have a pointer to A, which I have named PA. We do dynamic cast to pointer to A because we want to assign to pointer to A, right? And then we pass in PD, which is pointer to D. Then I can actually do a check. If I build a run, this will actually run. So I can do a check here. If PA is null pointer, then I print out a null pointer. I'll build a run here just to show you that we get null pointer. But this is an ambiguous cast here. So you can think for a second why this is, and I'll scroll up here. Remember that class D publicly derived from class B and class C, and class B and class C both derive from class A. I'll do Ctrl K, Ctrl F to format this here. So the point is, if we cast here to pointer to A, so PD is pointer to D. So if we want to cast to pointer to A, that is an ambiguous cast because we have two routes that we can go. So we can go to A from B or from C, right? Even though it's the same class, class A is the same class, but still. So one way that we can fix this, and you should avoid this right here, and to fix that you should do multiple upcasts for an unambiguous cast. For example, firstly we will cast to B, right? Or you can cast to C depending on what you want to do. So we will cast to B here, so that pointer to D is now cast to pointer to B, which we assign here to this pointer PB, and we pass that in to another dynamic cast, which we then cast to pointer to A, and then we will assign that to a pointer to A, right? So that is how you will avoid that ambiguous cast. Just an interesting example that I thought I'd show you, again, when you have multiple inheritance in this way. Again, this is a simple inheritance hierarchy, but of course you can have a very complicated one, in which case these ambiguities can really give you a headache. So you have to think about how you can solve that issue, and that is through using multiple upcasts. To visualize this, let's look at a class hierarchy. So we have class B deriving from class A, class C also deriving from class A, but class D is going to derive from class B and class C. Alright, so if we have a pointer to D, eventually we want to upcast so that we have a pointer to A, right? Now, which part are we going to end up with? Are we going to end up with a pointer to class A, which is part of class B, or a pointer to class A, which is part of class C? Because remember, both of those parts will eventually make up an object of class D. So when you instantiate an object of class D, you can have a class A as part of class B, which is part of class D, right? And the same thing with class A, which is part of class C, which is part of class D. So the thing is, as we have discussed before, class C can initialize the A class part of that base class in a different way. In the constructor, it can initialize its A class part maybe to 3, for example, whereas class B will initialize it to something else, such as 7 or whatever the case may be. So we have to kind of think of this in terms of what will eventually make up our object. So we have class D, for example, let's say that is an object where we'll have a class B part, and as part of that class B part, we will have a class A part, and also part of the class D object, we will have a class C, which will also have a part class A. And again, those can initialize their base classes in different ways. So what will we end up with? Will we end up with a pointer to the class A, which is part of class B, or a pointer to the class A, which is part of class C? And that is the issue that we have to solve. We may have to upcast multiple times to avoid an ambiguous cast. Another example of a class hierarchy, we have 5 classes here now. Class B and class C both deriving from class A as before, and class E is now going to derive from 3 classes, class D, B and C. So in this case, if you have a pointer to class D, you may have to downcast to class E before you can upcast again to class B and then eventually to class A, or to class C and then to class A from E again. So first you may have to do a downcast and then an upcast to avoid an ambiguous cast. So you may have to do 3 casts. Let's say you go down from class D down to class E and then up again to either class C or class B and eventually class A, right? But we can also do a crosscast if we have an object of type E on the heap. We can do a crosscast from D to B or C, for example, and then up to the class A. So instead of having to go down and then up, we can simply go to B or C directly and then up to A. So first you do your crosscast and then your upcast. So 2 casts instead of 3 in that way. An example of what this will look like in code: have classes A to E. Classes B and C publicly derive from class A, and then class D does not derive from anything, but class E does derive from class B, C, and D. Alright, so all of 3 of those classes. Then in the main function, I have a pointer to a type of D, and I allocate an object of type E on the heap. Now we have this example of an ambiguous cast. we do pointer to D, we cast the pointer to A. Alright, then we do this check. So if I build a run, we should get a null pointer here. That is going to be an ambiguous cast, so we cannot simply go from pointer to D to pointer to A. Now this allocation here works, this new E, where we do the allocation of the E object, and we assign that to a pointer to D because E derives from D. So as we've seen before, this is illegal in C++. We can assign a derived object to a base class object. In this case, E does derive from D, right? So next we do a downcast followed by an upcast. So this is one way of doing this. This is perfectly fine. Let's say we want to go from pointer to D to A, but the A that is part of B, right? So firstly you go from pointer to D to pointer to E. Then next we go from pointer to E to pointer to B. And then we go from pointer to B to pointer to A. And of course, if you want to do C, then here you would do pointer to E to pointer to C, and then eventually up to A. But you can also do this crosscast thing, where you go from pointer to D to pointer to B, for example, and then eventually you upcast. So first you do the crosscast, and then you do an upcast. Whereas here you would have to downcast first, down to E, and then eventually two upcasts. So with the crosscast, you can do two casts instead of three. I'd also like to note where you upcast. So here where we upcast, we can do this sort of thing here, where we do an implicit conversion. Same thing here where we upcast. Okay, so where we upcast, we can do an implicit conversion because that is fine. So where we upcast, this is fine, but where you downcast, it's best to use dynamic cast because that will make sure of the types. And then simply making sure to delete properly here to deallocate that heap object. Again, don't let this confuse you guys. If you have a pointer to a derived object, but the actual object on the heap is one of the base classes for that pointer class, then that's fine because you will have a pointer to a complete object even if it is not. So let's say you have an object of type B on the heap, but you have a pointer to type A. That's fine because that will be a complete object of the pointer type. So the object B will contain a part A, right? A full part of A. So that is why it is fine to have a pointer to A with an object of type B on the heap. And in the other way around, if you have a pointer to type of B, then of course you want a full object of type B on the heap at least, or at least that has a full part of type B on the heap. Otherwise the dynamic cast will fail, right? That is the point with dynamic cast. So I just wanted to reiterate that. And this is a concise example. I did not have virtual destructors for all of these classes. Of course you want to define virtual destructors for all of your classes. This was just a demonstration and I'm trying to keep it concise. Your classes in production will also be in their own files. Of course you'll have header and source files, so it will be a bit more all over the place. But again, this was just to demonstrate these topics. And so with that, we are going to wrap up this lecture. I hope you found it useful and interesting. Alright, and I will see you in the next lecture.